Boldly going where no science show has gone before. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with our all-star specialist in biology, cancer and everything else, Kat Arney. Hi, Kat.
Hello.
And also our kitchen science guru and physicist extraordinaire, Dave Ansell. Hi, Dave.
Hi, Chris.
Good to have you with us. I'm Chris Smith. And coming up this week, how scientists have developed a new and much safer way to test unborn babies for genetic problems like Down syndrome, and that's using, surprisingly, just a sample of the mother's blood. Also, after a lot of head-scratching, boom, scientists have uncovered the genetic cause of male pattern baldness. And is this the stickiest substance known to man? Scientists have copied the structure of the feet of a tiny lizard to develop an incredibly powerful adhesive. That's all on the way, and it's coming up shortly. Kat.
Thanks, Chris. This week it is our science question and answer show. We'll be tackling your science questions and teasers, including discovering whether lightning goes from the ground upwards or from the clouds downwards. And we'll also be looking into the workings of one-way mirrors, intriguing for the perverts out there, and finding out whether the Earth is getting heavier and where all the heat comes from to power volcanoes. Plus, we'll also be hearing how male hormones might have a lot to answer for, although it seems like the entire world financial situation's got PMT.
As the testosterone levels build up in these male animals, they become overconfident. And that's exactly what I was observing in traders during the dot-com bubble in New York. They take risks that are, quite frankly, stupid.
So that's how your hormones could control the money market, and that's all coming up later. Dave.
Thanks, Kat. And in this week's Kitchen Science, I'll be going back to basics to show you a splashing experiment you can do with a cup of tea. So if you want to have a go, make a cup of black tea or just get a glass of water, get some milk handy, and I'll explain what to do in a few minutes' time.
So it really is a bit of back to basics kitchen science this week, Dave. Thank you. It is an amazing experiment as well, so do have a go at that. It's coming up how to do it shortly. If you've got a science question for us, meanwhile, you can send it in. The email address is chris@thenakedscientist.com.
The Naked Scientist Podcast. Powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Very exciting news this week because researchers have found a way to test unborn babies for genetic abnormalities before they've actually been born, of course, and that's just using a sample of blood from the mother, because up until now, the only way to diagnose a baby's genetic situation was to go and physically get a piece of the baby, cells from the baby. That was either in the form of sticking a very long needle into the amniotic sac, which is the bag of fluid the baby develops inside, and then getting some of the cells out of that sac and analysing the DNA that's in those cells, or doing something called a CVS, a chorionic villus sample, where, again, a long needle is inserted into the placenta, which is made by the baby, and some samples of the tissue are taken away and again analysed genetically to see if the right numbers of chromosomes are there. But Steve Quake and his colleagues at Stanford University in California have come up with a much safer way to do this, just using the blood from a mother. Now, it all relies on a principle that was discovered a long while ago, actually, which is that when a mother is pregnant, you can find DNA from the baby in the mother's bloodstream. And this is because cells from the baby break off from the placenta and go around in the mother's bloodstream, and cells also fall apart in the placenta and their DNA floats out and goes around with the mother's blood. Now, why this is useful is that you can use that DNA to count how many copies of the chromosomes there are there, and therefore do the same as doing these risky procedures like an amniocentesis, which can trigger a miscarriage. This can't trigger a miscarriage, it's much safer. How did they do it? They take blood samples from the mother. In fact, in this small sample, they had 18 mothers who had a mixture of either a normal baby or a baby with a disease like Downs. And they then took the blood samples from the mother and used a very rapid sequencing technique to sequence the blood samples to work out which chromosomes they came from. And with all things being equal, what should happen is that you should have equal numbers of reads, in other words, pieces of sequence from every single chromosome, because there should be equal numbers of copies of all of the chromosomes. But if one of the chromosomes is there in an extra copy, for instance with Down syndrome, that's caused by an extra copy of chromosome number 21, you get more DNA reads than you should do. On average, from chromosome number 21, you get a blip on the graph, and this enables them to detect that, and therefore they can predict that there might be an abnormality.
But doesn't it get kind of flooded out by all the cells from the mother that are there? Surely you need very, very sensitive techniques to do this.
Well, apparently the cell-free DNA, which is DNA that's broken out of a cell and is just floating around in the plasma of the mother, up to tens of % of that can be of baby origin. So, in fact, you would be right, but the numbers of baby DNA molecules that are there are very, very high. And so you're actually recording a large amount of sampling from the baby, not just the mother.
Oh, that is really good news as well.
They're saying that the cost of doing this is half what it costs to do an amniocentesis. In their trial of 18 individuals, they got all of them 100% right. So now they want to do a much bigger trial and scale this up and see if it can be done as a valid replacement for amniocentesis.
And good news, because amniocentesis does carry a risk of miscarriage, so good idea. Anyway, on to another way to detect disease, and this is about detecting esophageal cancer. That's cancer of your food pipe, your gullet. And it's a growing problem in the UK because not only are rates rising dramatically from this type of cancer, but survival's often very low. And this is usually because the cancer is not spotted until a very late stage when it's much harder to treat. And now this technique, which is just so beautifully simple, I heard about this at the NCRI Cancer Conference last week. It's been developed by Dr. Rebecca Fitzgerald and her team at Cambridge University. Now, it all centres on detecting a condition called Barrett's esophagus, and this is a precancerous condition. It's usually caused by acid from your stomach coming back up into your gullet. And any of you out there who suffer from heartburn, this is what it is. So heartburn is experienced by about 1 in 10 people in the population. Then around 1 in 10 of those will go on to develop Barrett's esophagus. And it's in this case, the acid causes the cells of the esophagus to change, and this can cause them to become cancer cells. And this happens to around 1 in 100 people with Barrett's esophagus. They go on to get esophageal cancer. Now, currently, the way doctors pick this up is basically by shoving a telescope down your gullet and having a look around. It's a technique called endoscopy. So you have to go to hospital, have this done. It's not very pleasant, and obviously you have to go to hospital as well. But Dr. Fitzgerald and her team have come up with a fantastic technique that can be just done in the GP surgery. And basically, you have a little pill, it's about the size of sort of a big vitamin pill, tied to a piece of string. A nurse holds the string, you swallow the pill, she holds on to the end, that's the important bit. The pill goes down into your stomach, and there it expands to make a little rough sponge that's about, sort of the smaller, much smaller than a kind of a squash ball. You're talking about size of a raspberry, maybe. And then after a few minutes, the nurse will pull on the string, the sponge comes back up, taking a sample of cells from your esophagus on the way, and then you can look at those down a microscope. You can do things like antibody screening. And so far, this technique, they've just done a study for acceptability. So are people just prepared to swallow a sponge, have it pulled back up, because it does make you gag? And they found that people would much rather have this than to have an endoscopy.
Sure, but do you think it's going to be as sensitive as an endoscopy? Because when someone does an endoscopy, obviously you've got a very experienced set of eyes looking at the tissue. That's point number one. And point number two is you can then take a biopsy from areas that look dodgy, so that you can then target your approach to saying, I reckon that bit looks dodgy, I'm going to sample it. Whereas with your sponge method, it might miss that dodgy area and just take cells from elsewhere.
Well, the aim of the sponge is basically taking a whole sample of cells from up the esophagus. And the beauty of this as well is that you can use immunostaining, fluorescent staining, so you could potentially automate it to just highlight cells that look dodgy. The other thing is that endoscopy, you can't really do that many. And the problem is that lots of people have heartburn, 10th of those people go on to get Barrett's esophagus, and then 1 in 100 of those gets on to get cancer, and it's very, very high risk. So potentially this rough and ready screening technique could really save lots and lots of lives from the disease by catching it earlier.
Yeah, because it's nice and cheap, very quick. Do lots of people, and then the ones that you think might need another look, then you put your limited resources into them.
Exactly. It's a sort of a quick and dirty screening for a cancer that really we could do so much better in survival if we could diagnose it earlier.
And when will we see this potentially being wheeled out?
Well, there's a lot more trials needed to do, but Dr. Fitzgerald herself said potentially in 5 or 6 years you could see it, you sponge on a string down the GP surgery.
Thanks, Kat. Now, people have been fascinated by the ability of lizards called geckos to chase their insect prey, not just on the ground, but up walls and even across the ceiling. And various scientists have tried to emulate this, but until now they've not managed to achieve the same level of stickiness.
So how do geckos do what they do?
Well, if you get two atoms very close together, they'll attract one another with what's called the van der Waals force. This is what holds materials like wax together. But normally if you push two objects together, they don't stick because they're so rough that very, very small areas of them actually touch. Now, geckos get around this using millions of tiny hairs on their feet, and then each of these hairs branch into even tinier hairs at the ends. These are very flexible, which means that when the gecko pushes its feet onto the wall, a large portion of the tiny hairs are within an atom's breadth of the wall, so stick to it. And so a gecko can hold up about 10 newtons for every square centimetre. Now, scientists have been trying to use carbon nanotubes to do the same thing, but they haven't got very far. But Liming Day of the University of Dayton and colleagues have used these carbon nanotubes with very flexible and tangled ends. So if you push them onto a material, these tangled ends get very, very close to it and stick due to these van der Waals forces. Then if you try and slide it across, so a shearing force, these flexible ends kind of pull out and the area of touch gets bigger and bigger, and so they get stickier and stickier. And it also means if you want to pull it off, you only have to pull off one bit at a time. They unpeel, so the force required to remove it is much less. This material will support a force of about 100 newtons for every square centimetre, which is equivalent to 10 kilograms. But the material does need to be pushed on very hard, maybe about 50 newtons for every square centimetre, to make it stick well enough, which is far more than a real gecko's foot or other analogues that other scientists have made. This very large force is going to mean that actually using them for a Spider-Man suit is probably quite impractical, because you're never going to be able to push on hard enough to get the things to stick.
It's a shame.
It is rather. But it does have some other advantages. Because the nanotubes conduct electricity, it could be used instead of solder to attach pieces of electronics together. So instead of having to heat up metal and melt things together, you could just stick these nanotube things onto them. And also the nanotubes are unaffected by the vacuum of space, so unlike most glues. So you could use them in spaceships, so they don't degenerate with time.
So we might be coming closer to Spider-Man one day. Thank you, Dave. Now, an interesting paper this week has come out in the journal Cell Metabolism, and this is David Patsouris and his colleagues, and why this caught my attention is that it solves a long-standing mystery of medicine, which is, why is it when people put on a bit too much weight, why do they have a risk of diabetes? What's the link between putting on too much weight and becoming fat, and then getting diabetes or pre-diabetes conditions? And what this paper explains is that they have homed in on a particular kind of cell, which ironically is called a macrophage, which is Greek for giant eater. And these macrophages are part of your immune system. They go around the body, taking up residence in our tissues, and their job is to eat debris, dead cells, and invading microorganisms like bacteria, things like that. And they have found a chemical marker on the surface of some of these cells called CD11C, which singles out a population of these macrophages that they have found are responsible for causing this diabetic state in people who get too fat. So if you take mice and you give them the rodent equivalent of junk food, so they all become overweight, they then show all the cardinal signs of becoming diabetic, and you can see in their fat tissue increased numbers of these CD11C macrophages. What the researchers then did was to use a very clever genetic trick to remove selectively just those cells from the mice, and they immediately got better, and they showed better glucose levels, better insulin levels, that's the hormone that controls the levels of sugar. They also showed reductions of the levels of fat in their liver, which is another sign that a person has got too much weight on board. And also they showed a decrease in the amount of inflammation in their bloodstream. Chemicals called cytokines, which the immune system uses to signal, are higher in people who are overweight and in these mice, but as soon as they removed these cells, the levels went back to normal. The researchers don't know why these cells are doing this or how they're doing it, how they're making someone resistant to their own insulin, but it's a very important first observation. And what this suggests is it might be a new target for making a drug to stop people who are overweight having such a high risk of diabetes. We'll obviously have to wait and see to work out whether or not this does translate into a benefit to humans yet, though. But it's certainly very exciting.
It's absolutely fascinating because it's the first inkling that diabetes may be a disease linked to immune cells. And then also, particularly in my field, in the field of cancer, there's growing evidence that cancer may be due to sort of the immune cells not responding correctly to these problems. So very interesting. But now, here's some good news for any of our listeners who are thinning on top, obviously not including Chris and Dave here with your luxuriant heads of hair.
You like my wig?
Yeah, it's a good wig. Yeah, the Dolly Parton look really suits you. Anyway, there's 2 papers in Nature Genetics this week that reveal genetic variations that contribute to male pattern baldness, and that affects around a third of men by the time they're 45. And this is the classic pattern of baldness, sting here, where the hair starts thinning at the temples and on top, and it's thought to be hereditary in about 8 of 10 cases. Now, we've known for some time that there's a maternal link here, because they know that there's a gene on the X chromosome which you get from your mum if you're a man, and this is the basis of the idea that you get baldness basically from your mother's side of the family. But there has been evidence that there are other genes out there that are involved, but until now they haven't been tracked down. So there are 2 papers published at the same time. The first is from scientists at McGill University, King's College London and GlaxoSmithKline, and they found 2 genetic variations that, if found together, increase a man's risk of baldness by 7 times. And to find this, they scanned through the whole genomes of more than 1,000 men who'd been assessed for male pattern baldness. And they found 2 previously unknown gene variations on chromosome 20 that substantially increase the risk of baldness. And they confirmed these in more than 1,600 men. And they rather surprisingly showed that more than 1 in 7 men in the general population carries both of these baldness variations.
What do these genes do? Why do they make you go bald?
Well, at the moment, they don't know what they do. So what we've just found is variations in the genes. So the next bit of work is to try and track down to, are these actually in genes? Are these in control regions for genes? All we've done is found this difference in the genome. So we don't really know what genes they are yet.
Damn, I hope they solve it soon.
Yeah, exactly. And now there's another team of scientists at Bonn and Dusseldorf who've also carried out similar research and found the same regions popping up again. So this is intriguing because as we've known that there's a baldness gene on the X chromosome, this is the first gene that's been discovered for baldness that's on one of the what's called the autosomes. These are the chromosomes that everyone has. So, this explains why baldness patterns might be carried down from father to son. And also, maybe if you could identify who's likely to get hair loss, you could step in and prevent it in the future. But that's a long way off, sadly, chaps.
Now, at the moment, while solar cells are clean and environmentally friendly, the electricity they produce is still 3 or 4 times more expensive than electricity from fossil fuels such as coal. Now, part of the problem is the high cost of manufacture, but a less well-known problem is the cost of actually installing the things. I hadn't realised this, but because conventional solar cells are basically large and flat, they're like a great big sail, and if you want to attach them to the roof or something, you've got to hold them on really tight, because otherwise strong winds are going to blow them straight off. Now, a company called Cylindra is starting mass production of a solar cell which may solve this problem. Instead of using big flat solar cells, they're using very long, thin tubes, about 3 centimetres across, with a thin film semiconductor on the surface called copper indium gallium selenide, which, rather than being big and flat, then you paint the roof underneath white, so you get light reflected off the roof from underneath coming up onto the bottoms of the cylinders and light from the sun coming down onto them. And because they've got big gaps in between them, the air can rush through them so the wind doesn't pick them up, so you don't actually have to screw them down, so reducing the installation cost immensely.
Do they still generate reasonable amounts of electricity?
They're still about 13% efficient themselves, so probably not as good as a conventional one, but the big limit on the amount of solar power we can generate isn't how much area we've got, it's how expensive they are to build.
Sure, and how much do they cost?
They're not selling them on the street at the moment, but they should be intrinsically cheaper than conventional solar cells, as well as this huge reduction in installation costs.
Thanks, Dave. Let's hope so. It is The Naked Scientists with Chris, Dave and Kat. It's our science Q&A extravaganza where you ask the questions and we try and answer them. Got a couple coming up, which we'll be looking at in a second. But if you'd like to get in touch with the programme, the email address is chris@thenakedscientist.com.
Lifting the lab coat on the world's best science. The Naked Scientists.
We've heard from Rolly Mandelbrot, who's listening to us, and he says the pregnancy test that you mentioned for things like Down syndrome, how early into pregnancy can you do that test? Well, Steve Quake told me when I spoke to him last week that at the moment their tests have been done at 14 weeks, which is roughly the same time as you would do an amniocentesis, but he thinks he'll be able to wind the clock back even further and be doing these tests at 5 weeks after conception. So, in other words, very early in pregnancy, giving people much more time to make decisions about what they want to do, if they want to do anything about that. Kat.
Now, we have got loads and loads and loads of really great questions for you this week to get through. But first, we have some kitchen science. Now, Dave, what on earth have you got here?
Well, this week's kitchen science is incredibly simple. All I want you to do is get a cup of tea, a glass of water, and sometimes ways a glass of water is nicer because you can see what's going on a bit better. So fill up a glass with water.
So, filling up the glass with water.
Exciting bit, this bit.
This is all live and exciting. Real water.
And then basically get a spoon, pour a little bit of milk onto the spoon, then very gently just try and drop drips of water from about 4 or 5 centimetres up into the water, see what happens, and what colour, anything which comes back at you, what colour is it?
So you're dropping a single drop of milk into the cup of water or a cup of black tea, see what happens. As simple as that.
As simple as that, incredibly simple.
Am I going to be really amazed and impressed when this happens?
It is fascinating, the result, I reckon.
Excellent. Well, so there at home, this is a very easy kitchen science for you to do. Glass of water, teaspoon of milk, drop your milk. Does it matter what type of milk it is? Can it be...
Shouldn't do. I'd be interested to find out.
Semi-skimmed, anything? Well,
it may affect things, but it should have the same general result.
If you have more different types of milk at home, then maybe try those. So Dave will be explaining later on the show what you should see and how it will work. Chris?
And if you'd like to get in touch and tell us what you're seeing, the email address, if you'd like to email us in, chris@thenakedscientist.com.
Laying the facts bare. I say. The Naked Scientists.
Kat, we got a question here from Slack7639, who's emailed in to say, what about hormones, and including those that create nose hair? Do they also contribute to baldness? Is it all one and the same thing?
That is an absolutely fascinating question. I think the point about male pattern baldness is that it's that's really to do with sort of these genes that they've identified, and there are probably other genes that are involved in things like sprouting nose hair, sprouting ear hair, back hair, all those lovely things that happen to men as they get older, not to ladies at all. It's very nice. So presumably controlled by other genetics, and if any geneticists out there would like to do a study on the genes of nose and ear hair, you may get funded for it. So, I don't know if they're linked. We got some questions for you here, Chris. Okay.
Lucky me.
Yeah. We have a question from Wilness, who wants to know, does lightning go from the cloud to the earth or the earth to the cloud? What do you reckon?
Okay. Well, stats on lightning. Lightning is fascinating, actually, and the amount of energy being unleashed all around the world all the time is absolutely huge. The stats suggest that there's something like 2,000 thunderstorms raging all around the Earth at any given moment in time, unleashing about 100 lightning bolts per second. And if you tot up the amount of energy that they're bursting on and unleashing on us, it's something like 2 megatons of TNT equivalent every day. So it's a huge amount of energy. Where does it all come from? Well, it's pretty much down to static electricity. If you look at a big thundercloud, there are lots of particles called hydrometeors, which are ice crystals, for want of a better expression. And these are being jostled around, rubbed against each other, and rubbed against the air by updrafts within the cloud. And there are lots of different sizes. There are big ones and small ones. And for some reason that scientists don't quite understand, the big ones stay at the bottom and get a negative charge, and the smaller ones get a positive charge and they float towards the top of the cloud. So you've now got a big charge difference inside the cloud. And the concentration of negative charges at the bottom of the cloud creates an electric field which spreads out around from the cloud to involve anything that's near the cloud, and that includes the ground. So the Earth's surface then feels this electric field pushing on it, and this means that the negative charges in the surface of the Earth run away because they can move away, and this makes the surface of the Earth net positive. Now there's an attraction between the two, and the first thing that happens is when that charge in the cloud gets big enough to overcome the natural resistance of the air, it starts to form a thing called a leader, which is a very thin thread of electricity which runs down a bit of a disjointed, sort of crackly path down to Earth. And this starts ionising or stripping electrons away from molecules of gas in the air. And this creates a low resistance pathway between the cloud and the Earth. And once that leader gets to pretty close to the ground, then you will get a lot of ionisation of positive from the ground also coming up to meet it. Once you've made a connection, then you've got a very low resistance pathway, and a lot of that charge from the cloud will come zipping down. The electrons rip down the lightning bolt, creating a very big, what's called the return stroke, which then hits the ground and dissipates some of that energy. And interestingly, the actual size of the lightning strike, it's only about the size of a 1-penny piece across the actual pathway that the electricity comes down. And it passes a current of something like 20,000 amps, so a huge current which heats the air which it passes through to a scorching 30,000 degrees Celsius. So this is something like 5 or 6 times the surface temperature of the sun that it reaches. And this creates this enormous shock wave because it heats up so fast, and that's the thunder. So the answer to the question is that it's, strictly speaking, a dissipation of a lot of concentrated energy in the cloud, electricity, which is flowing away from the cloud to Earth or to another cloud or within the same cloud. So it's, strictly speaking, the energy is flowing away from the cloud, but it's a little bit of both. You've got this upwelling of positive charge near to the ground too.
We've got another taxing question for you as well.
Oh, not another one?
Yeah.
Can I ask you one first?
Oh, go on then.
Well, actually, I want to ask Dave something, because Colin Murray sent this a little while ago, and also Liana Serban said something similar, which is all about mirrors. So first of all, Dave, Liana Serban says, how does a one-way mirror work?
Okay, there isn't actually such a thing as a one-way mirror. It's not possible just to make light only go through something in one direction without going the other way, without using some really exciting electronics. Basically, the way I don't know if you ever sat inside a room when it's dark outside and it's light inside the room. If you look at a piece of glass, all you can see is your reflection. You can't see outside. That's because a piece of glass will always reflect maybe 10% of the light that hits it. But normally if it's outside and it's brighter, the light coming through it completely dominates, and so you don't really notice the reflection, you just see stuff going on behind it. But if it's really dark outside, there's no light coming from the outside, so all you can see is that reflection. Normally one-way mirrors are semi-silver. That means that there's some silvering on the back of them, so they're more reflective than a piece of glass, so maybe they'll reflect 80% of the light which hits them. So you can see the reflection very strongly. But if you're in behind one and it's very, very, very dark, so that you can't see that reflection, you can still see the light coming in through them. So you can see people in the light side, but the people in the light side can't see you.
So when you see a sort of detective story dramas on telly where you've got these detectives watching someone being interviewed and they're in a brightly lit room and the person being interviewed is in a brightly lit room, that's a myth.
That wouldn't work, no.
Just wouldn't work. Colin Murray has written in this very interesting question, which is how many times can an image be reflected between two facing mirrors? So if you have two mirrors facing each other and you put an object between them, and if you look in from the side, you can see the picture of, I don't know, your hand or something going off to infinity almost, can't you?
Yeah.
How many times, he's asking, will it carry on bouncing the image back and forth between the two?
Fundamentally, that's basically what happens when something hits a mirror. Light gets reflected. Depending on how good your mirror is, a certain portion of that light will get absorbed by the mirror, but most of it will get reflected. Normal mirrors around the house will reflect about 70% of the light. Really high-quality mirrors they use in optics labs in universities and research places, they can reflect sort of 99.9% of the light. So basically, it just depends how faint you can still see that light. So with normal mirror, you probably won't be able to see it after 10 or 20 times because it'll get so dim. But with really high-quality mirrors, maybe several hundred, several thousand.
Brilliant. Thank you very much, Dave. We'll have to reflect on that one a bit more later. Kat, got a question here for you from Andre, who says, why can a finger be passed through a flame and not burn? It's a stunt that people do to impress their mates. How do you do it?
Yeah, this is a fascinating thing to see. The first time I ever saw this done, this was done by my vicar at church. And it's like, this man has come from God if he can do this. It's very impressive. The thing behind this is that basically candles aren't that hot. And also the other trick is to do it fast and through the right part of the flame, because you need to know a little bit about how candles work. And it all boils down to convection. Heat rises. So the top of a candle is actually much hotter than the bottom of a candle. If you ever try holding your hand over the top of a candle, you'll find out extremely fast. It's very, very hot. It's about sort of 600 degrees. But you can actually pass your hand through the bottom of the flame because all the hot air is rising up, and the bottom of the flame is where the cold air from the room is being sucked in. So actually, the bottom of a flame is quite cold. You can stick your hand through, get a bit of soot on it, but you can do that so long as you do it at quite a quick speed, and especially if your hand's a little bit wet or your finger's a little bit wet, because then you'll just kind of burn off the water rather than burning your hand.
Brilliant. So now you can go and impress your mates with that, but don't try it with a blowtorch or something.
No, not Bunsen burner, not a blowtorch, only a candle.
Steve Higgins is on the line. He's in London. He's got a question for you, Dave, about escape velocities and firing bullets into orbit. Hello, Steve.
Hiya.
Welcome to The Naked Scientist. What do you want to ask us?
Basically, it's been bothering me for a while, this one, but assuming there's no wind resistance or, no air resistance and no wind, and that you had a gun powerful enough, could you shoot a bullet straight up and hit a satellite which is in stationary orbit?
Okay, do you mean a geostationary satellite straight above your head, or just anyone in orbit?
Yeah, so what if you knew there was one up there directly above your head in geostationary orbit and you aimed, could you hit it?
Okay, if you fire a bullet up fast enough, you will be able to get it up past the geostationary orbit. Geostationary orbit's up at about 36,000 kilometres, and basically the orbit takes exactly the same amount of time as a day, so it looks like it's above our head all the time. However, that still means that the satellite is moving at about 11,000 kilometres an hour. So I don't know if you've ever heard of people trying to shoot ducks or clay pigeons. If something's moving fast, you've got to shoot in front of it because it takes a while for the bullet to get to the clay pigeon, so you've got to aim in front of it. Yeah. So if the satellite was straight above your head, you'd actually go miles and miles behind it by the time the bullet got there. But if you aimed ahead enough and you calculated it all right and did lots of exciting calculations, you would be able to hit it if you fired it out fast enough. If you escape velocity, it's about 11.2 kilometres a second. In that case, if it's going that fast, it will get out of the Earth's orbit entirely. So you would be able to go through it, and you ought to be able to hit it.
But you'd need a pretty powerful gun, wouldn't you, Dave?
Definitely. No one's built one fast enough yet.
Thanks for your question, Steve. Brilliant question. It is The Naked Scientist with Dr. Chris, Dr. Dave and Dr. Kat. It's our science phone-in extravaganza. If you'd like to ask us any questions, our email address is chris@thenakedscientist.com.
Distilling the best science. The Naked Scientists. For more information, look us up online at nakedscientists.com.
This is The Naked Scientists, and this is Chris, Dave and Kat in the studio. Today we are taking on your science questions. Hit us with them. Still to come, our lovely Diana Carroll is going to find out why songs get better the more you hear them, and we're also making a pot of black tea to drop milk into for our kitchen science. But first, the credit crunch. It's happening all around us. It's like the entire world has got PMT. House prices are falling. The prospect of borrowing money even to buy a house or a shoebox in London is a virtual impossibility. But why is this happening? And what's science got to do with it? Well, it turns out that two human hormones, testosterone and cortisol, both of which are known as steroid hormones, could be partly to blame for this complete chaos that we've been seeing recently. And we sent Mira Senthilingham to find out why.
In light of the current economic situation, I've come down to the City of London, to the trading floor of GFI Group. I've come here to find out what underlies the actions taking place here to determine our market. Could human behaviour be playing a vital role in the state of our economy? Well, to help me look into this is John Coates from the Judge Business School at Cambridge University, who's here with me now. Hello, John.
Hello.
So, John, how do the markets really work?
Well, essentially what we're doing in markets are buying and selling assets issued by either private companies or the government. And the job of traders is to buy and sell these securities, and in deciding whether to buy or sell them, they have to make an assessment of the return they're going to make on these assets over the life of holding them and the risk involved.
So you've been looking into the physiology of traders in the City of London. What have you been looking into?
We've been following up a hunch I had when I was working on Wall Street during the dot-com bubble. I was struck by the fact that traders at the time were acting very different from the way they acted before the bubble and after the bubble. They were displaying classic symptoms of mania. They were overconfident, they had racing thoughts, diminished need for sleep, and they were carrying themselves in such an odd way I began to suspect that there was a chemical involved. The second thing I noticed was that women were relatively unaffected by the frenzy surrounding the dot-com bubble. During that time, I was splitting my time between the trading desk and Rockefeller University on the Upper East Side, and there I came across a very, very powerful model that's been tested in a number of different animal species, and I thought this model may be applicable to the financial markets. In this model, it's called the winner effect. Two male animals go into a competition. Their testosterone levels rise in preparation for this competition. The winner comes out of that competition with even higher levels of testosterone, while the loser comes out with lower levels. The winner may go into the next round of competition with an already elevated levels of testosterone, and this can give him an added advantage. It has effects on muscles and the cardiovascular system, but more importantly, it affects his confidence and his appetite for risk. So he goes into this competition with a slight edge. It's what happens in the end game of this model. It's really interesting. As the testosterone levels build up in these male animals, they become overconfident. So, for example, they go out in the open too much. They pick too many fights. They patrol areas that are too large, and they neglect parenting duties. So they suffer an increased rate of predation. And that's exactly what I was observing in traders during the dot-com bubble in New York. They take risks that are, quite frankly, stupid.
So how did you go about actually testing this in city traders?
I got access to a trading floor in the city, and we took salivary steroids from a group of traders over a 2-week period to test that steroids were, in fact, responding to the money they were making and losing in the market, and whether this in turn was affecting their trading performance.
And what did you find?
We found that the traders, if they had high testosterone levels in the morning relative to their median levels, they made a lot more money for the rest of the day than they did on days when they had low testosterone.
Well, when most people think of testosterone, they obviously associate it largely with males. So does this then mean that females are relatively unaffected?
Women have about 10% of the testosterone as men, so it's entirely possible that they're not subject to this kind of overconfidence.
But you were also looking into levels of cortisol as well, weren't you?
That's right. In the current environment, that may be the more interesting steroid. When the market turns around and turns into a crash, what can happen is that cortisol, which is a stress hormone, can become elevated in the bodies of traders. And cortisol, if you're exposed to it chronically at high levels for a long period of time, it can have a devastating effect on both the mind and the body. In terms of affecting traders' decisions, what it can do is affect the memories you recall. You tend to recall bad memories, negative precedents. You tend to see risk where maybe there is none. You become fearful, you feel anxiety, and we think that decreases a trader's appetite for risk. So while testosterone is causing people to take too much risk in the bubble, cortisol is causing them to take too little risk in the crash.
So what do you think the current situation is now? Do you think that there are going to be higher levels of cortisol in the traders at the moment?
It's not only how far the market has fallen, but it's how long it's been falling. So these traders have been under stress for almost a year and a half now. Their cortisol levels must be elevated. I'm sure that there's a very good chance it's affecting their decisions.
And you were mentioning that long-term effects of cortisol will have long-lasting effects on their mind's activity. Is this something that companies should think about?
I guess so, yeah. I mean, it's something the Bank of England should be thinking about. Economics is built on the assumption that economic agents are rational, that they respond to price signals. So if you increase the price of something like money by raising interest rates, people will stop buying securities, but they don't in a bubble. On the flip side, during a crash or a depression, they lower interest rates, and economic agents are supposed to respond to that by buying assets so they look more attractive. But if these steroids are reaching such a level in our bodies that we become price insensitive, then monetary policy may no longer work. And in fact, that's what we see.
And so do you think if the banks and the companies understood this physiology a bit more, that they could work together, say with neuroscientists, to try and get out of the economic situation that we're in at the moment?
We're in a bit of a mess at the moment. Cortisol is a hormone that responds not just to like loss or injury, loss being in this case losing money. It also responds more powerfully to situations of novelty, uncertainty, and uncontrollability. And so within banks, I think it's extremely important, although very difficult to do, of course, to create an environment that minimizes the trader's feeling of uncontrollability. Managers think they have to be sort of proactive, as they say in business speak, to show that they're doing something to improve situations. And usually what they're doing is threatening to fire people. And that's exactly the wrong thing you should be doing. We need some positive shock to come into the system of the very sort they're talking about right now, like the bailout package passed in the U.S. last week and being discussed this week in Britain and Europe to break this downward spiral of risk preferences.
So it's all down to men's hormones. That was John Coates, who's a senior research fellow in neuroscience and finance at the Judge Business School at Cambridge University. He was talking to Meera Senthilingam about how our hormones can make the difference between going for gold and going broke on the stock exchange. Kat.
We've got a couple of questions here for you, Chris, about the Earth. And David Hubble in the US wants to know, is the Earth getting heavier? Are we putting on weight as a planet?
Yes, but perhaps not for the reason that he was suggesting, because people often think that as we increase our population, the weight for the people comes from nowhere and people just weigh more. The Earth, therefore, weighs more. That's not true. The Earth is a sort of sealed unit, if you like, where all of the weight that was on it to start with doesn't go anywhere and you don't make weight from nowhere. So people have got to gain weight by taking weight from elsewhere on the Earth, eating food that's come out of the Earth, for instance, and putting that into their bodies. But the planet as a whole, does that get heavier over time? The answer is yes, it can. And every year, Earth gains about the weight of 2 aircraft carriers landing on it, 2 HMS Ark Royals, 40,000 tonnes worth of debris lands on Earth. You can demonstrate this for yourself if you put a big plastic sheet or a white sheet on your grass on the garden on a nice day, leave it for a few hours, and then run a magnet over it. And you can often find specks have just fallen down from outer space and landed on your magnet. So debris, dust and other stuff raining in from space contributes a huge amount of weight to the Earth every single year. So yes, we do gain weight.
And there's another question here from Glenn who wants to know, what keeps the Earth's core so hot?
Oh, a combination of things. One, the Earth's actually quite a big planet, say, relative to Mars, which is a bit smaller. So there's a lot of heat that was in the Earth to start with, because when the planets were first forming around the Sun in what's called a protoplanetary disk, a lot of the swirling, spinning material was crammed together and squeezed together, and it had a lot of heat from that, those frictional effects. But also the Earth has what's loosely termed a georeactor, where there are lots of radioactive compounds in the Earth, and as these radioactive compounds break down and decay, they produce heat, and the heat is obviously concentrated in the core of the Earth and then filters up towards the surface. And because the Earth's a big planet, it's got a big core, it's got lots of radioactive decay going on. Some of the heat that we're seeing is because the Earth is sustaining its own heat by radioactive decay.
So basically like having a little nuclear reactor in our core.
Absolutely right. Dave, got a question for you. Clinton's on the phone. Hello, Clinton.
Good evening.
Welcome to the Naked Scientist.
Oh, thank you. Good evening. Yes, so I'm wondering if you could tell me how high above ground level bees can fly.
I think there's a big difference between how high bees can fly and how high they bother to fly, because there's not a lot of point in a bee flying more than a few hundred feet above the ground.
They can't be bothered.
because all their food's on the ground, where they live's on the ground. There's not a lot for them up high. But how high can they fly? You can find bees several thousand metres up in the Himalayas, and they're flying around there, so they're quite happy flying there. I think the biggest constraint is the temperature, because the inside of a bee reaches nearly 50 degrees centigrade while it's flying, because all the chemical is using lots of energy. All those chemical reactions need to be happening very quickly, so it needs to be very hot. And as soon as the temperature drops, they don't happen fast enough, so the bee can't flap its wings fast enough, so it'll fall out of the sky. So I think the biggest limiting factor is the temperature rather than the altitude.
Thank you very much to Clinton. Great question. Kat, another one for you. Graham Ramsey in Whitehills says, wants to bake a Christmas cake. Have you put some kind of thermocouple, in other words, a temperature measuring device, in the middle of the cake? And this is because you are an expert cake baker. I've tasted your cakes. He wants to know, is there a temperature at which the inside of the cake ought to be cooked?
There probably is, because out there in the world of the internet, you can buy cake temperature probes. I'm not sure off the top of my head what the correct temperature for a Christmas fruit cake is. You can also use the much cheaper toothpick method, where if you stick a toothpick in, does it come out with the mixture stuck on it? But I guess, that would depend on the temperature that you wanted to bake your cake at. And because things like, the sugar will get hot, all these kind of things. So there will be a temperature, and I'm not sure what it is.
I guess also, again, because cooking is chemistry, it might have to stay at that temperature for a certain amount of time. So just because it's got to that temperature doesn't mean it's already cooked yet.
Yeah, my very nerdy brother-in-law's a scientist, and certainly when he does meat on the barbecue, he has a temperature probe that's all electronic to make sure that his steaks are cooked properly.
Whatever happened to the fact that we're all still here? Humans have been evolving for 6 million years since we split away from our ape-like ancestors, and we didn't need all these things then, and I don't think we need them today. Dave, question here from Pat in Lowestoft. He says, if they test atomic bombs again, could it throw the Earth off its axis?
It shouldn't do anything particularly big to at the Earth's axis. Although a nuclear bomb is very big, very powerful, can release energy equivalent to millions of tons of TNT. Compared to the actual weight of the Earth, that's not very much energy. The amount of energy you'd need to flip the Earth axis over would be absolutely immense, and it's just not enough energy there. And also, in order to do that sort of thing, you'd actually have to get some push it. You'd basically have to build a rocket. So you'd have to build a huge nuclear-powered rocket, throw a load of stuff into space, which would produce enough momentum to actually give a kick to the Earth, which a nuclear bomb doesn't do. When a nuclear bomb goes off, nothing actually leaves the Earth. It just lifts some stuff up, and then it falls back down again.
Thank you, Dave. I think probably the best evidence is that if you look at the power unleashed in the Boxing Day tsunami, which was an enormous amount of energy, on par with probably something nuclear, I would say, this did make the planet jitter a tiny amount, but it didn't actually destabilise us on our orbit or anything like that. So I think probably the answer is definitely going to be no to that one, isn't it? Kat, this is a wonderful question from Martin Fennell, which is appropriate because it's a question about plants and herbs and things, in this case chili, and he said, what happens when a mild chili plant gets pollinated with hot chili pollen?
Okay, now it's an interesting question, and the misconception is if you grow two plants close together, a hot one and a cool one, that their peppers will be hot on the cool plant. In fact, potentially their seeds could give rise to hot peppers in the next generation, because the heat of pepper is determined by capsaicin and the genes that make capsaicin. And,
Too much capsaicin
exactly. And these are actually dominant genes, so effectively if you breed a hot plant to a cool plant, then the next generation, those seeds will potentially be hotter, yes.
But the fruits of the plant that are making them, they're just the genes of the plant that's growing the chilies.
Yeah, they're just the carriers for the seed, those plants.
So in other words, you've got to do the breeding experiment and then grow the next generation.
Exactly. You have to take the F1 generation and plant them, and then you'll get sort of an interesting blend, depending on the peppers that you've bred together and how those genes interact.
Dave, Hedra in Linton says, can a magnifying glass lose its power?
I guess the magnifying glass works because light goes slower in glass than it does in air. So when it hits it, it bends, and a magnifying glass is very carefully shaped so that all the light which hits it coming from one point is focused down into another point. In order to reduce its power, as in reduce how strong, how sharp, how closely it can focus, that would involve changing the shape of the magnifying glass or changing the density of air, which isn't going to happen very much. So unless you can't change the shape of the glass, what you could do is change how much light is focused into one place. So if you're trying to burn a piece of paper with magnifying glass, if the glass got scuffed, then more of the light would get scattered out, unless it would get focused down to a point. So that, for some definitions of power, that could reduce it, but not how closely it could focus.
I suppose it's worth bearing in mind that glass is a supercooled fluid, so it does flow over time. So if you kept your magnifying glass for long enough, eventually it might go slightly out of shape and therefore lose its power. But I mean, that's kind of really speculative, isn't it? Kat?
We got one final question for you. In this world of superbugs that we're terrified of, Jeremy Mode wants to know, are soaps and sanitisers breeding superbugs as well as antibiotics?
No, they're not. And the reason I would say that is because when we use soaps and things, we're washing our hands and that kind of thing, what the soap is actually doing is dislodging dirt, grease and effectively bacterial food from your hands, as well as the bacteria themselves. So this is assuming you're obviously using them to get rid of bacteria, because your hands are a breeding ground for bacteria, because they're covered in the vestiges of your last meal, they're covered in bits of you, they're covered in sweat, and this is a bacterial banquet. So if you come in with the soap, what the soap does is to knock off all of that debris and those places where bacteria could lurk, making the hands much harder to provide a home for bacteria. And it doesn't actually matter if the bacteria become resistant to the soap, because what the soap is doing is making the hands into the equivalent of a Sahara desert instead of a bacterial oasis, and that's why effectively washing your hands is good to get rid of bugs.
And Jeremy also wants to know, are things like the soaps and sanitisers, are they affecting the evolution of our immune system? You know, this theory that you need a certain amount of bugs and yuck to have a healthy immune system.
This is a huge can of worms, and the answer is possibly. There's a concept called the hygiene hypothesis, which suggests that the immune system needs educating from a young age in order to tell the difference between friend and foe, and the way it does that is by exposure to the things in the environment that we need to know are friendly and the things that are not friendly. And some people suggest that non-exposure to the things that are both friendly and moderately nasty, if you don't let your immune system learn to recognise those, then the immune system almost twiddles its thumbs and says, well, if I'm not doing that, then I might as well react to everything. And so you get this hyperactive immune system which responds to things that it should actually be ignoring, and that's when you get allergies. So it's a possibility, but it's difficult. This is The Naked Scientist with Dr. Chris, Dr. Dave and Dr. Kat. We're taking your science questions and hopefully answering them for you. If you'd like to join in, the email address is chris@thenakedscientist.com.
Keeping you abreast of the world's best science. The Naked Scientists.
You are listening to The Naked Scientist with Dr. Chris, Dr. Kat and Dr. Dave. And we just had a quick comment in from Edsel about the magnifying glass story. He says, a magnifying glass will certainly lose its power if you drop it on some concrete. So, yes, it certainly will. But now it's that time where we invite the charming, the glamorous, the ever-intelligent Diana O'Carroll back to the studio for our question of the week. Hello, Diana. You're going to talk to us about annoying pop songs.
I am, although I'm not very glamorous today. I'm probably wearing the most hideous set of clothes that I actually own. But
you see me behind? You see me.
Anyway, so on with annoying songs. I'm dealing with songs I love to hate today.
Hello, my name is Jay. I live in Indonesia, and this is my question. Why do songs grow better with repeated listening?
So why is it that songs that initially sound rubbish still make it to number one?
I'm Adrian North, and I'm Professor of Psychology at Heriot-Watt University in Edinburgh. The reason why people generally seem to like music, or one of the reasons, is to do with the level of complexity in the melody. Now, by complexity we mean basically by how erratic the melody is, or how varied the melody is, or basically by how weird sounding, if you like, the melody is. So, for example, a lot of modern classical music to many people would sound to be quite weird, quite complex, and so on, whereas, for example, a lot of modern dance music has got a fairly repetitive melody, and so most people tend to regard modern dance music as being relatively low in complexity. Now, we know in the grand scheme of things that people like moderately complex music that chops and changes a little bit, but not too much. But of course, that's got big implications for how music fares with when it's repeated. Of course, when you hear a piece of music the first time, you don't really know what it's going to do next. When you hear it a second time, you've got a better idea of what it's going to do next. And when you hear it the third, fourth, fifth, sixth, seventh times, then you start to have a very good idea how that melody is going to progress. So in other words, the more often you hear a piece of music, the less complex it seems to you. And so what that means is a piece of music that was originally too complex for you, when you've heard it a few times, becomes moderately complex and you start to like it. Conversely, a piece of music that was moderately complex and popular the first time you heard it, because you've heard it more times, it becomes simple, it becomes less complex. Now it becomes too simple for you and you don't like it anymore. So in other words, liking for music is determined by complexity, but complexity decreases with the number of times you hear a piece of music. That change in the level of complexity changes how much you like the piece of music in question.
So it turns out your brain can find those hooks that draw you into the rhythm of a song the more you listen to it. Of course, this won't really work if the song is so thrash metal that it has no hooks. Well, if you're planning to use your iPod to listen to Slipknot 43,000 times, then you'll need to charge it up.
Hi, this is Alvin Raj from Cambridge, Massachusetts, and my question is it really better to let a battery completely run down before charging it?
So if you know the best method for dealing with rechargeables and why it works, then tell us all about it. We love to hear what you think, so drop us an email to chris@thenakedscientist.com or write us on our forum at thenakedscientist.com/forum.
Thank you, Diana. That's Diana O'Carroll with this week's question of the week. And talking of songs that get better as you listen to them, we'll be hearing a song from our very own Kat Arney, because Kat has launched her own album. It comes out this week, and we've got a rare sample of it for you and details of how you can get hold of it if you really like it.
Bringing the facts to bear. The Naked Scientists.
This is The Naked Scientist, and now it is time to find out what's going on in kitchen science. So earlier on in the show, we asked you to go and get a glass of water or a mug of black tea and drip a teaspoon of milk into it. So what's going to happen, Dave?
Well, we might as well find out by actually doing it.
Yes, let's find out. Live, exciting,
science.
Not going all over the desk. Is going all over the desk.
Shh.
Okay, so now I've got a spoonful of milk, and I'm going to very gently try and drip it into this water from about 4 or 5 centimetres up. So what do you see happening?
So what you can see, as well as the milk going down into the water, when the milk hits the surface of the water, you see this white splodge come back up. Now, what's all that about?
Well, you get sort of this jet coming up in the middle, and in fact sometimes you get a droplet coming off the top of that jet, which flies upwards and then crashes back down again into the middle. Now, what's going on is that when the milk hits the water, it's got a whole lot of energy, and it's a round sphere roughly, hits this water. It's being stopped, and as it does it transfers energy momentum into pushing the surface of the water down, and as it does it, it gets flattened out very flat. And because milk mixes with water quite well, it sort of sticks to the water. So essentially you've got this sort of big flat depression. Sometimes it can get almost hemispherical. Of milk splurged over the top of water. Then basically you've got a hole in water, it's going to want to flow back inwards. Snap backwards, so both gravity and surface tension is going to snap it backwards, so you get a wave travelling into the centre, and when it hits the centre you get two waves coming from opposite, or a whole circle of waves coming from different directions, all colliding in the middle. And that's got a load of energy which goes into shooting both milk upwards and downwards, because you actually get a jet downwards as well. Sometimes you get a beautiful little smoke ring going downwards, which is lovely. And so you get this jet coming upwards, and it's almost entirely made up of milk, about a third the size of the original droplet, shooting upwards, and this little droplet coming upwards, and then it crashes back down again.
So, Dave, that is absolutely fascinating if you're particularly into making cups of milky tea. But what's the application of this in the real world? Why is it so important to know about this effect?
Well, the physics of how drops interact when they hit things is incredibly complicated, because it changes with the surface tension of the drop. So if you added washing up liquid, it would change it. It would change with the viscosity of the drop. So if you were dropping something like treacle into water, it would behave entirely differently. And these sort of things are incredibly important when you start dealing with drops hitting things in a real-world situation. So if you're thinking about how to keep something clean, if you want to keep a surface clean, you want the drop to bounce off so it doesn't get wet and dust stick onto it. Or if you want making an inkjet printer, because an inkjet printer works by shooting little droplets of ink at a piece of paper, and you really don't want them hitting the ink, hitting the paper and bouncing off.
And we get a bit of a messy print there.
It's not going to be ideal, is it?
Not at all. And I understand that you've been quite busy with your amazing flash high-speed camera. What have we got on the website?
Yes, I've managed to borrow a lovely high-speed camera from the Department of Physics, and at www.thenakedscientist.com/kitchen science you'll be able to see some lovely videos I've taken of it, and this is one of the nicest I've got here.
Now, this is great. Video on the radio, everybody. And here you go. You can see a white drop comes into the water. You can see it kind of go out into a hemisphere and squidge back in. And it is really phenomenal. This drop of milk gets shot up into the air and splats back down into the milk, into the water. That is really incredible.
I just keep watching them. They're so pretty.
Beautiful.
So there you go. Who would have thought you could find the amazing science of how droplets behave in a cup of tea? Thank you very much to Dave. There are more experiments like that, kitchen science experiments, on our website at nakedscientist.com/kitchen Kitchen Science. Now, I've got a quick question from Les in Over, who says, are green potatoes poisonous, or is this a myth? The answer is yes, they are, Les. Potatoes actually entirely are poisonous. They're a member of a family called the Solanaceae, and they make a toxin which is a neurotoxin called solanine, and if you eat 5 kilos of potatoes, that's actually a fatal dose. So watch it, Kat, next time you're feeling peckish. 5 kilos of potatoes is bad. But the solanine tends to concentrate in the areas that are exposed, and those areas also give us a sort of traffic light that they've been exposed. They go green because they're exposed to light, and that's chlorophyll. So it's not the greenness that's the bad for you bit, it's the fact that potatoes that are exposed to light make this, because solanine is also poisonous to insects and pests. It's the potato's way of protecting itself. It's just worse for them than it is for us. So by making solanine, they can stop themselves being eaten, especially if they're exposed to the sun. So if you see a green potato, it's got these glycoalkaloids, solanine in it, and it could poison you. But stay away from 5 kilos worth and you'll probably be okay.
Absolutely. Very quick question for you, Chris, here. Are hot air hand dryers an infection risk? They're always meant not to be.
Well, potentially, because when you're in the bathroom and you've washed your hands, if you don't wash your hands very well and you've still got bugs and viruses on your skin, and then you put them under the cleaner, this will blow anything, including a fine mist of water, off of your hands. And if you look at the floor under a hand dryer, you'll always see it's covered in water anyway. So you've got lots of water landing on the floor with any bugs in it. Plus, what they're doing is creating lots of air currents in the room that could also stir up bacteria from around the toilet, from around the urinals, or whatever sort of toilet you're in, and circulate them. And this means you might breathe them in. So I think actually it's worse than having just a towel, or the best thing probably is paper towels that you take one, wipe your hands on it, and then chuck it away.
Or on the back of your trousers.
And
can I do my plug now?
Kat has been dying to tell us about this. Now, this is pretty unusual, though. I mean, you've got someone who works in science, but also has this sort of doppelganger existence as a musician.
Yeah, no, I've been playing for a while in a band called Sunday Drive. It also has someone with a PhD in physics in it. But yeah, my band Sunday Drive, we're launching our first album funded by the Arts Council, and our launch is actually here in Cambridge next Friday on the 17th. So if you'd like to come along, and you can ask me science questions while I'm there, you can buy your tickets from www.junction.co.uk, because it's at the Junction, the J2 Theatre. There's going to be comedy, poetry, burlesque, loads of music. And
that's just you, is it?
Just me, yeah. And we'll be flogging our new album called In the City of Dreadful Night.
How long have you been recording it for?
We've been recording it since February this year, but we've been together for a while. So yeah, it's all very exciting.
Is this stuff you've distilled from the last X number of years working together, or is this you sat down in February and said, right, we're going to make an album and it's all new material?
It's new material for us. It's sort of a year or so old, so quite a lot of new material. One or two old songs have snuck on there, but yeah, it's very exciting. And if we've got time, maybe we can hear a little bit, and this is our first single, which is called Heroes. See if it works. That's our very own Dr. Kat Arney's band, Sunday Driver. And if you'd like to hear more of her music and get hold of a copy, then why not pay them a visit? They're on the web at sundaydriver.co.uk. Well, that's it for this week. Thank you to our production team, Ben Valsler, Diana O'Carroll and Mira Senthilingam. We're back next week with a look at the science of nuclear fusion. We'll be asking, can we recreate the process that powers the sun here on Earth? And we'll be putting that question to the team behind ITER, the International Thermonuclear Experimental Reactor that's being built right now in France. So if you'd like to ask them a question, then do send it to us, chris@thenakedscientist.com. And don't forget, Dr. Dave and I have also published a new Naked Scientist book that's called Crisp Packet Fireworks, and details of that are on our website at nakedscientist.com/kitchen science. You can get a copy in the US and in the UK via Amazon. So if you do like The Naked Scientist and you'd like to support us, then do please consider picking up a copy in time for Christmas. Have a great week. Thanks for listening, and goodbye.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.